Okay, we're coming into our last topic here in Chapter 3 on differentiation, Section 3.9, and the last thing we want to talk about is differentials. So I don't know if you remember, when we first talked about different notations for the derivative, we said dy dx, right? dy slash divided by dx. Think of that as just notation, right? So we know that dy dx is the same thing as f prime of x, but now if I actually think of dy dx as a fraction, right? dy divided by dx equals f prime of x. Then I could actually multiply it by dx. So dy is actually f prime of x times dx. So this dy here and this dx are actually differentials when we think of them separately. Before it was just notation. And then this is the picture of what they are when we're thinking of them. Okay, so remember dy divided by dx, or dy dx, is the slope of the tangent line, right? So the slope of the tangent line would be change in y over change in x. So the change in y for the tangent line is dy, right? But what is dy? Well, it's whatever, it's f prime of x dx. So in this case, at x equals a, it's f prime of a times dx. Notice that dx will always be the same as delta x. But if I want the actual change along the curve, that's delta y. And delta y, which is this distance from the curve, the change in y along the curve is not the same as the change in y along the tangent line, because the tangent line is only equal to the value of the function right at that point, and then it changes as I get further away from a. So I'm just trying to give you an idea of what the differentials mean with a graph here. So how do we use those guys? All right. Take a look at this. Make sure you go through it and understand it. But essentially, this delta f is the same as the delta y that I put up in the other picture. So this is dy. I don't know why all of a sudden the author started calling them df, but this is dy, right? dy is f prime of a dx. Delta y would be the change along the curve. F of a plus dx minus f of a. So if we want relative change, you just divide by f of a. And if you want percentage change, you divide by f of a multiplied times 100. So these are changes along the curve. This is change along the tangent line, which would approximate the change along the curve. And these are relative changes, right? So this is the actual relative change along the curve. This is the approximated using the tangent line of the relative change. Percentage change along the curve, this would be the approximate percentage change using the tangent line. So for example, 52 here, our last example, we want to use differentials to approximate the cubed root of 7.97. So the first thing you have to ask yourself is, what function are they asking me to approximate? So you have to kind of say to yourself, well, they want the cube root of something, so the function I'm actually trying to approximate is a cube root of x. In this case, I want x to be 7.97, but the function I'm trying to approximate is cube root of x, which is x to the 1/3. So what is f prime of x? F prime of x then is simply 1/3 x to the minus 2/3, the power rule, right? Or if I write it in the root notation, it'd be 1/3 times the cubed root of x squared. Okay? So then you think to yourself, well, I want to pick a value for a that is close to the value of x that I'm trying to approximate. But when I plug in that value of a, these functions, the function and its derivative, are easy to evaluate. So the value of a that's close to the value of x, 7.97, that makes these guys easy to evaluate is a equals 8. Okay, now, what's the distance between a equals 8 and x equals 7.97? That's my dx. So to get from 8 back to 7.97, I have to subtract 0.03. So dx would be minus 0.03. So again, why did I choose x equals 8? Or a equals 8? Because that's close to 7.97. And it's easy to evaluate in both the function and its derivative, because f of a is just a cube root of 8, which we know is 2. F prime of a is 1/3. Cube root of 8 squared, so that's a cube root of 64. Cube root of 64 is 4. So that's 1/3 times 4, or 1/12. And those are easy to evaluate compared to the 7.97. If I plug those guys in, those would not be easy to evaluate. So if I think about this as a linearization problem, right, the f of x is approximately equal to my L of x. But remember what L of x is. The linearization was f of a plus f prime of a dx. Well, this f prime of x is the dy. This f prime, this f prime of a times dx, this piece of it, of the linearization, is the dy. Okay, so in other words, that's it right here. But the bottom line is the cube root of 7.97 then is approximately equal to f of 8, which is 2, plus 1/12 times x, I'm sorry, 1/12 times dx, right? This is f prime of 8 times dx, which we know was negative 0.03. So put that all into your calculator, you get 1.9975. And then for fun, again, I plug in the cube root of 7.97 to my calculator, and I saw that it was 1.997497. So linear approximation is pretty good, huh? The error can actually be shown to be what mathematicians call big O of delta x. I just tell you that. That's not in your textbook. In case anybody talks to you about big O notation, this is not something I'll ever ask you about. The error will decrease at the same rate that delta x decreases. It's just, that's what this means. Big O of delta x means that the error gets small based on the size of delta x getting small. Okay? Otherwise, that's how I use differentials. Really no different than linearizations, just that we think of the dy and the dx as to what they are.